Okay, we are going to continue with chapter 12. In the last video, we looked at we looked at shear stress, which we represented with a tau, or a tau sub s. Shear stress is something that occurs when you apply a moment or torque to a shaft. The other thing happens is that it twists. We're going to measure that twist with an angle. Now, shear stress, being a stress, is measured in PSI or KSI or pascals or kilopascals or megapascals or any other metric prefix pascals. The angle, though, no matter what units we're using, always must be in radians. So it needs to be in radians for our formulas to work. However, most measuring devices that an engineer would use to measure an angle are going to be in degrees. So for communication purposes, we're going to want to describe angles in degrees, but when we plug into formulas, it has to be radians, otherwise the formula does not work. So there are a couple different ways we can represent the formula for angle of twist. Theta is equal to the shear stress times the length over G, which is the modulus of rigidity, times C. We talked about C in the last video. It's the distance from the centroid to the outer edge. So for a circle, C is simply equal to the radius. Or perhaps a more useful arrangement of this formula is TL over JG. This is probably a more commonly used and more useful form of this. So this is going to give us, when we plug into here, it's going to give us the angle of twist in radians. I really can't stress enough how important that is. The units are going to be in radians. So let's take a look at an example, like example 12.7. In this example, we have a 38 millimeter diameter. So our diameter is equal to 38 millimeters. Now, when I work with metric units, I like to take everything to the base unit. So rather than saying 38 millimeters, I want to move this decimal place 1, 2, 3 times and say that that's equal to 0.038 meters. The length of it is 2 meters. And it is subjected to a torque. Scroll down here. To a torque, so big capital T torque is equal to 600 Newton meters. We want to know, in this problem, it's actually going to ask us for both the shear stress as well as, part B, the angle of twist. So let me just kind of strike a line right down here and use the other half of the screen here to begin. Let's start by looking at the shear stress. So in order to calculate the shear stress, we're going to need to know J, because our formula for shear stress, and this is something we went over in the previous video, shear stress due to a torque is equal to TC over J. So we're going to need to know J. What is J? J for a solid shaft, not hollow but solid, is equal to pi d to the fourth over 32. So that would be equal to pi times our diameter right here is 0.038 meters to the fourth. We're going to divide that by 32. So the polar moment of inertia, J, is going to be equal to, let's see, this is a lot of zeros. Let's count them up. It's 6 zeros. 1, 2, 3, 4, 5, 6, followed by a 205. And those units are in meters to the fourth. So pretty small polar moment of inertia. So the shear stress is going to be the torque of 600 newtons times C. That's going to be half the diameter. So if the diameter is 0.038 meters, then the distance C from the centroid to the outer edge is going to be 0.019 meters. It's half of that. And then let's see here. J goes on the bottom, and that is our 0.000000205 meters to the fourth. And so if I solve that formula, I get 55 million, and rounding it to three significant figures would be 600,000 Newton per meter squared. And I was just wondering why my units aren't canceling out. That's because up here I forgot a little meter. This is a torque up here, so it's Newton meters, not just newtons. So I have 2 meters on top. That's going to cancel out 2 of these and leave me with square meters. That cancels out, that cancels out. So we're left with Newton over meter squared. So the units work out. So that is that's the shear stress caused by this torque. I can clean up those zeros with a metric prefix and say that this is 55.6. A Newton per meter squared is equal to a Pascal, and we've got 55.6 million of them, so that's a megapascal. So that answers part A right there. The shear stress is 55.6 megapascals. Put a big box around that. And now we can look at part B. What is the angle of twist? I'm going to scroll down a little bit farther and say that our angle of twist is equal to TL over JG. The torque was 600 Newton meters. The length given in the problem statement is 2 meters. J, the polar moment of inertia, is based on the shape, and we've already calculated that. That is 0.000000205 meters to the fourth. And G is a property of the material, so we're going to have to look that up in Appendix G. The material in this example problem is steel. And so let's look that up and see what we get. So the specific variety of steel in this problem is ANSI 1020 hot rolled. And as I look that up in Appendix G for the metric, the column for modulus of rigidity, the units given there are kind of odd. They're in megapascals times 10 to the third. So essentially they're gigapascals. And the value in the table is 79.3. So that's 79.3 megapascals times 10 to the third. Well, megas times 10 to the sixth. If we multiply 10 to the sixth by 10 to the third, we get 10 to the ninth. So that would be like moving this decimal place 9 places to the right. So that'd be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So put a comma there, there, and there. So it's going to be 79 billion 300 million pascals, or a pascal is, let me erase my parenthesis. Let's see here. Where's my eraser? Let's erase. Oh, that erases my background too. Don't need to do that. Let's fill that back in with some black. Close enough, I guess. Let's go back to my pen and change my color back to yellow. And so that's a pascal, which is a Newton over a meter squared. I like to do this to make sure all my units are canceling out. So I've got 2 meters on the top, and actually the meter squared here is on the bottom. It's Newton per meter squared. So those 2 meters are going to cancel out 2 of these. The 2 of these up here are going to cancel with that one down there. And then I'm left with newtons over newtons, which actually leaves this as unitless. So radians are kind of funny units. They're almost like unitless units. So everything should cancel out. All the meters cancels out, all the newtons cancel out. And what I'm left with is 0.0738. And these units are in radians. Okay, so this formula gives us radians. But the thing is like, how big is a radian? That's really hard to visualize. That's not really the way we typically communicate angle measurements in the real world. We do that with degrees. So it makes more sense as a final answer to take the answer that the formula gives us, which is in radians, and convert it into degrees. So if I've got 0.0738 radians, I want to convert that. My conversion factor would be, for every pi radians, there are 180 degrees. And so 0.0738 times 180 divided by pi gives me 4.23 degrees. So that's a lot easier to visualize, 4.23 degrees. That's not really a lot, but depending on the application, that may or may not cause a problem. So it's important to the engineer to know how much this steel shaft will twist if we apply this torque to it. So there we go. There's our answer for part B. There's our angle of twist. One last thing I'll leave you with here in this video, and we'll include this in future videos as well, is as an engineer you typically have to design the size of a shaft. And so if we're designing, we need to choose the diameter. And there are 2 formulas here that you will find useful. The diameter equals the third root of 16t over pi times the allowable shear stress. So that's for stress. And for angle of twist, the diameter needs to be equal to or greater than the fourth root of 32 TL over pi times theta times g. We'll be using these formulas in future videos.